This is solving linear systems of differential equations by diagonalization. Because that can be kind of a hard topic, I'm also going to go over a little bit of the theory in this video. So, what we have here is a equation x prime equals a times x, where x prime and x are vectors, and a is this coefficient matrix. This system is coupled, so there's no way to detach each element of x from this coefficient matrix and get it by itself in x prime. And so what we need to do instead is we need to diagonalize a, and that will let us decouple the system. So a is diagonalizable if a has n linearly independent eigenvectors, if a is n by n. So if A is 3 by 3, it needs 3 linearly independent eigenvectors, 7 by 7, 7 linearly independent eigenvectors. If A is diagonalizable, then there is a matrix P that diagonalizes A. So P diagonalizes A by D, the diagonal matrix, equals P inverse times A times P. And so if we meet this condition, then this is true. And if this is true, then we can solve this system by diagonalization. So what we will do is we will construct the matrix. We will make this substitution. We'll let x equal p times some vector y. And so if x is equal to py, let's substitute that in. So then x prime will be py prime. And so this system of equations now becomes py prime is a p y. And if we multiply on the left on both sides by p inverse, we have p inverse p y is p inverse a p y. Sorry, p inverse p y prime. But p inverse p is I, and p inverse ap is d. So this just reduces to y prime is dy. And since D is a diagonal matrix, this means that y prime 1 is some constant lambda 1 times y1. And y2 prime is some constant lambda 2 times y2. And so on, all the way up to yn prime is lambda n times yn. And these lambdas are going to be the eigenvalues of A. So when you diagonalize A, this matrix D, the elements are the eigenvalues of A. But from here, all of these differential equations are separable. And so we can solve them with separation of variables, and we get y1 is some constant c1 times e to the lambda 1t. And we can do all that all the way down to yn is c1 e to the lambda n t. Once we have this, we know what p is, so we can construct, and this gives us y. So this will give us y. We know what p is, so we can construct x from here. X is equal to py. And once we've constructed x, we have solved the system of differential equations. Okay, so let's go ahead and find d, p, y, and x. So because we already know how to find eigenvalues and eigenvectors, I'm only going to show the process of finding the first eigenvector, and I'll just tell you what the other one is, and you can verify that for yourself. So Of course, to find the eigenvalues, we need to solve the characteristic equation of A. So the characteristic equation of A in this case will be 1 minus lambda times 1 minus lambda minus 1 over 4 equals 0. So if we expand this out, we will get lambda squared minus 2 lambda plus 1 minus 1 over 4, or lambda squared minus 2 lambda plus 3 over 4. These would be 0, and we can factor this into lambda minus 3 halves times lambda minus 1 half. 0, so our eigenvalues will be lambda 1 is 3 over 2, and lambda 2 is 1 over 2. So I'll go ahead and find the eigenvector associated with lambda 1. So that eigenvector will be found using the augmented matrix A minus lambda 1 I bar 0. And if we construct that, 1 minus 3 over 2 is negative 1 over 2, 1 over 4, 1. 1 minus 3 over 2 is negative 1 over 2. 0, 0. So then we can multiply this first row by negative 4. So we'll do negative 4 row 1 becomes the new row 1. And multiply the first row by 2 and add it to the second row. And 2 row 1 plus row 2 becomes row 2. That should eliminate the second row. So after this, we will have 2, negative 1, 0, 0, 0, 0. And so from here, we can see that 2k1 minus k2 equals 0, or k1 is 1/2 k2. So this tells us that our eigenvector k1 associated with lambda equals 3 over 2 should be 1, 2. Or that could be one of our eigenvectors. I'll use that one. So if we were to do it the other way, so this is associated with lambda 1 is 3 over 2, and then for lambda 2, that's 1 over 2, and its associated eigenvector k2 will be negative 1, 2. Okay, so now we have those. We know that D will be P inverse A P, but we also know that the elements of D will be the eigenvalues. So D will be 3 over 2, 0, 0, 1 over 2. And we know that P will be the matrix made up of the concatenation of the eigenvectors in the same order that they appear in D, or in the same order that their associated eigenvalues appear in D. So P will be 1, 2, negative 1, 2. So then we have P, so we should be able to find Y and X. So we know that y prime is dy, and we can write this as y1 prime, y2 prime equals 3 over 2, 0, 0, 1 over 2 times y1, y2. And so, then, we can write this as y1 prime is 3 over 2 y1. And y2 prime is 1 over 2 y2. So from here, we can get y1 is c1 e to the 3 over 2 t. And y2 is c2, e to the 1 over 2 t. So that gives us y is c1 e to the 3 over 2 t c2 e to the 3 over 2 t. So now we have that, and we also know that x is py. So x is x1, x2. That is 1, 2, negative 1, 2 times c1 e to the 3 over 2t c2 e to the 1 over 2t. And so we can write the vector x as c1 e to the 3 over 2t times 1, 2 plus c2 e to the 1 over 2t times negative 1, 2. And this x is the solution to our system of differential equations.